tell it to you. So what is the dimension? What is dimension of any space?
Number of independent entries.
Yes, sir.
Just
Number
one
of
moment.
independent.
I have started this thing and let me just. Yeah. So for scalar matrices, the set of scalar matrices in any dimension, I'll use three-dimensional space for now. It will be of the form lambda, 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 and everything else is 0. Right? This is scalar matrices. Or I can write it as lambda times I3, where I3 is the standard, the identity matrix. But what is lambda times I3? As lambda varies. So isn't this just span of the singleton I3? Are you with me
Yes,
so
sir.
far?
Yes.
Yes, sir. Sir,
Right.
so dimension of I3 is 3, na?
Dimension of I3 is dimension of the singleton I3 is 1. So you have to see how many elements are there in the set. I3 is just one element, right?
Okay,
Sir,
sir.
I think she's confused with, the actual dimension, like 3 by 3 total 9 elements are there and the vector
Yeah.
one.
So it's not that. So suppose if you suppose you have this sort of subspace in R3. So this has dimension 2 because there are two vectors, even though these are vectors in 3 space. These are actually just two vectors which span the subset. So you have to look at the size of the spanning set, not the way the elements look in that. Okay, so number of elements is 2 over here, number of elements is 1 over here. And when there are two, first you have to verify that they are linearly independent. Also, in this case, obviously they are. So this would have dimension 2, this would have dimension 1. Okay,
Okay, sir.
so
Yes.
yeah, maybe if there's still doubt, we'll take it at the end. Okay, and yeah, we will be looking at orthogonality, linear independence, and all that in this session. There's no recap as much, but we'll be using the notion of what an inner product is. There were 3 axioms that we used when we were talking about the inner product last time. So you don't need to remember the 3 axioms in all its details. And since this is the first time you are seeing the abstract notion of an inner product, if you get confused, just think of it as the dot product. Assume that it is the dot product, but it works for any inner product in general. We also looked at a non-standard example of an inner product, and we also saw examples where the notion of orthogonality and the notion of length also is very much dependent on the inner product. There was I think 1 0 and some -3 0 or something which were orthogonal in the specific example we had chosen last time. So whether a vector is orthogonal to another vector or not, orthogonal meaning perpendicular, meaning we'll discuss that over here. That very much depends on the notion of the inner product that is there. So assume that you have an inner product space, meaning you have a vector space V with vector addition plus with scalar multiplication dot and an inner product, which means it's a function from R cross R to, V cross V to R. It takes two vectors and spits out a real number, just like the dot product. It's the generalization of the dot product. Now, what is the angle? This is something that we had seen last time. What is the angle between, let's say, vectors V1 and V2? Do you remember the formula for cos theta?
Yes, V1 dot V2 divided by norm of V1 and norm of V2.
Yeah, V1 dot V2 is in the specific dot product case, but in general, it is the inner product of V1, V2 divided by the norm of V1 times the norm of V2. So this is what we had already seen last time. So if norm of the inner product of V1, V2 is 0, then what is theta?
90.
Yeah, or pi by 2. Conversely, if theta is pi by 2, then also you will get that inner product is 0. So inner product of two vectors being 0 is the same as the angle between them being equal to 90 degree. So if V1, V2 is 0, the inner product of V1, V2 is 0, then V1 and V2 are said to be orthogonal to each other. Orthogonal, sometimes even perpendicular. More commonly, orthogonal is used. So it is the same as saying the angle is 90 degree, or sometimes people also use the name perpendicular. Now let's take an example. Let's take something like 1, 2, 3, and let's say 2, 5, k. Now k is some unknown. Suppose it is known that these two vectors are orthogonal to each other. V1, V2 are orthogonal, then find the value of k. How would I go about doing it? So whenever the inner product is not specified, you have to assume that this is the standard inner product, which is just the dot product. So what I need is these are orthogonal to each other. In other words, the dot product of the two vectors is 0. But what is the dot product of these two?
Individual elements multiplied and there's some 1 into 2 plus 2 into 5 plus 3 into k.
So it's 2 plus 10 plus 3k. This has to be 0, right? So what is k?
4.
-4.
-4.
K is -4. So for k is equal to -4, you will have that these two are orthogonal to each other. So in general, if you want to check whether two vectors are orthogonal to each other or not, you will just take their dot product and see if it is 0 or not. And if in this case, we are not actually checking if they're orthogonal, we are saying that it is given that they're orthogonal and we have to find a variable. And this is how you do it. Now, this is just for two vectors, but of course, this can be generalized to a finite number of vectors. A set of finite vectors. Let's say we have n vectors. V1, V2, Vn is said to be an orthogonal set. If Vi, Vj is equal to 0 for all ij. Well, I not equal to j. So what does this mean? If you take any two pair of distinct vectors from the set, then their inner product has to be 0. So can you give me an example of an orthogonal set? Of course, this two element set would be an orthogonal set by default because there's just one choice of pair of vectors that you can take. So another example is, let's take the standard basis in R3. Is this an orthogonal set?
Yes, sir.
So if I take the inner product of the first vector with the second vector, I get 0, which can be easily verified. Second with the third, I'll get 0. Third with the first, also I will get 0. So this is an orthogonal set. But notice that this is also a maximal orthogonal set. What do I mean by maximal orthogonal set? I cannot
Basis.
add any vector to this and it remains orthogonal. Right now, if I take any other xyz and add it to this set, it will have non-zero inner product with one of them, right? Do you see that?
Yes,
Did you
sir.
understand the statement that I made?
No,
Yes,
sir.
sir.
Sir, can you please repeat once?
Okay.
Yes, sir.
So I take these three elements and I know that these three elements form an orthogonal set. Now I add another element, a fourth element. Let's just call it XYZ. Is it possible that this four element set, is there a choice of XYZ such that this four element set 1, 0, 0, 0, 1, 0, 0, 0, 1 and XYZ is still an orthogonal set? So for that, what do I need? I need that this is orthogonal to this, this, and this. If the set that I obtain after adding this also remains orthogonal, then I need orthogonality with each of the three original vectors, right? But that would mean that this is a zero vector. Why? Because inner product of x, y, z with 1, 1, 1, 0, 0 is just x. It gives you x is equal to 0. Let me just write that. So xyz dot 1, 0, 0 is equal to 0 implies x is equal to 0. Xyz dot 0, 1, 0 is equal to 0 implies y is equal to 0. And xyz dot 0, 0, 1 is equal to 0 implies z is equal to 0. So you'll get this the zero vector. So of course, if I add the zero vector, it will always remain orthogonal. But yeah, we take non-zero vector. So addition of any non-zero vector will force it to be not orthogonal. So in that sense, it's a maximal orthogonal set. Not too much to worry about this point. As far as you understand that 1, 0, 0, 0, 1, 0, 0, 0, 1 is an orthogonal set, that is sufficient. This maximal orthogonality will come a bit later. Another example we'll just see using the set that we had already seen earlier, right? 1, 2, 3, and then we did 2, 5, minus 4. Can I add another vector to this so that I get an orthogonal set? Can you give
Yes,
me?
sir.
Can you give me a choice of vector?
Any linearly independent vector, sir?
But I don't think any linearly independent vector will work. So take, for example, 3, 0, minus 1, something like that. So this will be orthogonal to this, but this will not be orthogonal to this.
Okay.
Right?
Yes, sir.
So it's not easy to construct orthogonal sets. Actually, I don't even know how, well, you'll have to solve a system of equations if you want to go do it the right way. But at least this is an orthogonal set. Let's just, no. This is not maximal orthogonal. There is a choice of third vector which can be added to this so that it remains orthogonal. So if this will make more sense once I talk about linear independence and orthogonality.
Sir, 0, 0, 0.
0, 0, 0 is not something that you add because that will that is trivially orthogonal to everything that you can just keep adding.
Sir, then how can we
You're
find any sort of orthogonal sets, vectors, sir? Because how would we solve the equation?
Yeah, so that will come maybe even in the second session, not even over here. So it'll come. This answering this question will be done before the end of week 8. How do I get it? Okay, how do I get this third vector? So now let us leave it blank, but I will tell you that there is a vector. I will not give you the vector, but I'll just tell you that there is a vector. So yeah.
Sorry to interrupt you, sir.
But
I just want little clarification.
yeah.
Sir, you told cos theta is equal to inner product divided by norm of this, sir. Isn't it, sir? Just scroll up, sir.
Could you repeat your question?
Sir, can you just scroll up the cos theta definition which you given, sir, earlier in the first piece, sir?
Yeah.
Yeah, so cos theta is equal to inner product of v1 v2 divided by norm of v1 v2, sir. For sir, for better understanding, for just for layman understanding, sir, we can say that inner product is equal to dot product and the norm is equal to the magnitude, isn't it, sir?
Yes, yes, yes. In the easiest or most trivial case, that is the case. That is the thing, and you can think of it that way in this session. If a usual inner product is too abstract, just think of it as a dot product.
Okay, and so the
Dot
norm is
product
the
and the length of the vectors.
no, and the norm is the length of the or the magnitude of the vector.
Yes, magnitude of the vector. Yes.
Fine.
So
Thank
if you took this as a plane, then there used to be one thing used to have, right? Like the cross product would give you a vector perpendicular to it. Something like that used to be there.
Cross product, yeah, but we are not discussing cross product over here.
No, I'm just
That-
saying, like, would that,
Yeah. There is another operation, but that is also specific to 3 dimensions and
Right.
all that. Yeah, but dot product is doable in any dimension of Rn itself, and then we generalize it to any vector space as we did last week. But okay, back to orthogonality. One of the advantages of orthogonality is seen in the following result. An orthogonal set is linearly independent. So typically, how would you check if something is linearly independent? You would set up equations. So take, for example, this itself, 1, 2, 3, 2, 5, 4. Okay, if it's a two-element set, you can see that one is not the multiple of another. If you have, let's say, a three-element set, if this is, I don't have this third vector, so I cannot actually give the same example. But the usual procedure for verifying linear independence of a finite set of vectors is that you set up this equation CIVI is 0, summation CIVI is 0, C1V1 plus C2V2 plus so on up to CNVN is 0. And you try to solve for this CIs. The CIs are the variables. And if CI is identically 0, if 0 is the unique solution, then the set of vectors is said to be what?
Linearly independent.
Linearly independent. So if summation CIVI, so okay, consider V1 to Vn, a set of vectors. And then if I write summation CIVI is equal to 0, and then I solve for it and obtain that Ci is equal to 0 for all I, this is if this is forced, then this Vi is linearly independent, right? V1, V2, Vn then is linearly independent. I write it as Li. But proving this statement would involve setting up a system of linear equations using Gaussian elimination or whatever tool is at your disposal and doing it. But if it is known, suppose is an orthogonal set. Suppose the given set is an orthogonal set. And whether it is orthogonal or not is a far easier check than setting up the system of equations and doing Gaussian elimination, correct? So if it is an orthogonal set, then linear independence comes for free. So I'll give a proof of it. It is not very important, but later on, while finding the coefficients, this will be even more relevant. So if I set up the system of equations, summation CIVI is equal to the 0 vector, I can take the inner product on both sides using any basis vector Vj. Inner product of 0 with Vj is 0. The dot product of 0 with any vector is 0. Similarly, inner product of 0 with any vector is 0. So I'm just taking inner product with one of the basis vectors. It's whatever Vj. Let's do V1 first instead of taking an arbitrary vector. Let me just do V1. Now, what happens when I do the inner product? The inner product is linear, right? It's bilinear. So this becomes summation Ci Vi V1. At any step, if you have a doubt, stop me. So this I'm just using bilinearity in the first, or bilinearity in both arguments. If you have sums of vectors and inner product, you can do the inner product and then take the sum. If you have scales of vectors and inner product, you can take the inner product and then do the scaling. This is one of the axioms of what an inner product is. Or if it is more comfortable for you, look at it like in the case of dot product also this happens. So, but what happens over here? It is known that V1 up to Vn is an orthogonal set. So unless I is equal to 1, so in this summation there are n terms. Each of them has an inner product of Vi with V1. So the first term would be C1 times V1 with V1. And then you have C2 times V2 with V1. And so on Cn times Vn with V1. This is equal to 0. This is the equation that you have set up. This is the system of equations that you have set up. But what happens is this is 0. Why? Because it's an orthogonal set. Everything else is 0 also because it's an orthogonal set. The inner product of V1 with any other Vi other than V1 itself, that is 0. So the only term that survives is actually C1 times norm of V1 square is 0. But norm of V1 square is not 0 because this is an orthogonal set. By definition, when you say orthogonal set, you will not include 0 vectors in it. Okay. So this would imply that C1 is 0. So I got C1 is equal to 0 by taking the inner product of the initial equation with the vector V1. I can do the same thing with V2. I'll get C2 is equal to 0. And so on, I can take the inner product with an arbitrary Vj and get Cj is equal to 0. So repeating the procedure n times will give me that Ci is equal to 0 for all I. So orthogonality implies linear independence. This is a quick proof of that. Do you understand the proof?
No, sir. This last part.
Okay, so did you get the part until C1 is equal to 0?
No.
Okay, so which step do you have a confusion in?
The C1 equal to 0 just above it.
How do I get from this to this?
Yes, sir.
So what is the definition of an orthogonal set? Every two pairs of vectors, distinct vectors, are orthogonal to each other. So you will have Vi Vj is equal to 0 for all I not equal to j. This is the definition of orthogonality. So in this summation, you see that the first one has an inner product of V1 with V1. The second term has inner product of V2 with V1. The third term has V3 with V1, and so on up to the last term, which has Vn with V1, inner product of Vn with V1. But only V1 with V1 survives because everything else is, you're taking inner product of distinct elements of this orthogonal set. So each of them is actually 0.
Yes, sir.
Is that all right?
Yeah.
So what you're left with is just the first term, which is C1 times length of V1 square or norm of V1 square, that is equal to 0. This gives you C1 is equal to 0. But I can start this with summation Ci Vi with V2 is equal to 0 also, because on the other side you have 0 anyway. So this would give me C2 is 0. You can follow the same proof and you'll get C2 is equal to 0. And so the same thing you can repeat for all combinations or all choices of Vi and get that Ci is equal to 0 for all I. Even if you don't understand this in its entirety, it's fine. All you need to know is orthogonal implies linearly independent. Okay, so when you are given a basis, or when you are given a set of vectors and want to see whether it is linearly independent or if it's a basis, you can first look for orthogonality. You can see if it is orthogonal. If it is orthogonal, then you don't need to go about the hassle of solving the system of linear equations. Orthogonality is a much easier check. So, of course, there is a cautionary statement. Linearly independent does not imply orthogonal. So you could have a set of vectors which are linearly independent but not orthogonal. You can easily manufacture things like, say, 1, 1, 1, 0. These are clearly linearly independent, but they're not orthogonal in the standard dot product.
Sir, can
What
we
it
say
says is
all
just,
orthogonal
yeah,
sets are linearly independent?
yeah, that's the result here, right? Any orthogonal set is linearly independent.
Yes, sir. Got it.
So if by chance the set that you are given to check for linearly independence is an orthogonal set, then you're happy. Then you can very quickly say that it is linearly independent. But if it is not orthogonal, it does not mean it's not linearly independent. That is the point of this caution. Something could be linearly independent while not being orthogonal, like this. Okay. So orthogonal sets, they are a special case of linearly independent sets. So they're more there are more conditions, as in, well, all orthogonal sets are linearly independent, but linearly independent sets are a bigger class, right?
So,
Definitely by this, yeah, go ahead.
so with the orthogonal test that we are doing with these vectors, and we are assuming that the calculations will be simplified, but I see that orthogonal computation is also very intensive.
No,
So,
no, orthogonality, see, take for example this, you just have to do 1, 1 dot 1, 0, right? This is 1, this is not orthogonal. Now, if I give
so,
you 1, 1, yeah, go ahead.
so we are checking linearly independence with orthogonal, but
Okay,
the
let me give you an example which may make it clear. So you have, let's say, 1, 1, 0, 1, minus 1, 0, and 0, 0, 1. Okay, you want to check if this is a basis. I mean, this is a three-dimensional three vectors in a three-dimensional space. So linear independence would mean basis. I want to check linearly independent or equivalently if it is a basis. How would I go about doing it in the classical fashion? Either I do C1 times 1, 1, 0 plus C2 times 1 minus 1, 0 plus C3 times 0, 0, 1 is equal to 0. I try to solve for this set of equations wherein I'll get C1 plus C2 is 0, C1 minus C2 is 0, C3 is 0. But these three together will give me C1, C2, C3 is equal to 0. So the only solution to the linear combination of the three vectors being 0 is the trivial solution. So these are linearly independent. This is how you have been showing linearly independence so far. Is that correct?
yes, sir.
Okay, but now that I know that orthogonal sets are linearly independent, I'll just look at the dot product between this and this. What is the dot product between first vector and second vector?
0.
It is just 1 minus 1
Zero.
plus 0. It is 0.
Yes,
What
sir.
is the inner product between second vector and third vector? Clearly 0. And first vector and third vector, that is also 0,
Zero.
right? And that was a
Yes,
much
sir.
quicker check. You can just eyeball it. You don't even need to have a paper for it, right? At least in this case.
Yes, sir. Yes, sir.
Do you get my point that in general, this is lesser computations? So if I
Yeah.
look at, this is 0, this is 0, and this is 0. Am I getting it correct? Yeah, I've made all the choices. So this implies that the given set is linearly independent. Let me call this S or something. S is linearly independent. Of course, there's another method. You could construct the matrix 1, 1, 0, 1, minus 1, 0, 0, 0, 1, and then compute its determinant, which is equivalent to solving this system of equations. But even that is more computations than this, is what I would argue. Computing inner products is typically simpler, as long as, well, you have not if you have the standard dot product, it is much simpler. So to expand more on it, S is orthogonal, and therefore S is linearly independent. There you can say it this way. Okay, so there is advantage to having orthogonality, but this is not the only advantage, as we will see. Now we look at what is an orthonormal set of vectors. So orthogonal means pairwise you have to have orthogonality. What is orthonormal set of vectors? Do you have any guesses?
Norm is equal to 1, sir.
Yeah. A set V1 up to Vn, which is orthogonal, meaning mutually orthogonal. Every pair of distinct vectors are orthogonal, and norm of Vi is equal to 1 for all I. So here both the notion of length and angle come into play. The angle between any two distinct pairs of vectors has to be 90 degrees, or their inner product has to be 0. In addition to that, I need that each of the vectors in the set has length 1 or norm 1. So that's that. Why orthonormal set? So this is what we will see. And yeah, before we go into why orthonormal set or the advantages of an orthonormal set, there's another note that I want to do. If, let's say, V1, Vn is an orthogonal set, then V1 by norm V1 and so on up to Vn by norm Vn, this set is orthonormal. So let's go back to the examples. So here, the most trivial orthogonal set that we saw, is this an orthonormal set?
Yes.
Yes, sir.
Orthonormal also. But the other orthogonal set, so this is an orthogonal set also that we had seen. This is not an orthonormal set, correct? But here I've left something empty, so I'll come back to that example later, maybe in the next session even. But let's see this other orthogonal set that we wrote down. Is this an orthonormal set?
No.
One of the element is orthonormal, sir.
Yeah, but I want it for all. No? This is for all I.
Yes, so it's not ortho.
It's not. So let me just denote this by dagger. So in example this, S is not orthonormal. But since the only obstruction to orthonormality is the length, I can just divide by the length and it will be orthonormal. How will I do it? So what were the vectors which were not orthogonal? Which were not unit length?
So we can just divide the vectors with lengths more than one with their lengths, right? In that case, we'll get the length
It
equal
doesn't
to.
matter. It doesn't matter if it is more than one or less than one. You just divide them by their norm.
Yeah. Yes.
If you divide by the norm, you consider this set. So 0, 0, 1 was the last vector. Divided by its norm also for good measure. Consider this set. Now, what is the norm of 1, 1, 0?
Root 2.
Root 2.
Root 2.
So you take 1 by root 2 times 1, 1, 0. And 1 by root 2. Again, this will just be 1 by root 2. And fortunately, the third one has norm 1 itself, so there is nothing to divide. This is orthonormal. First of all, is it orthogonal? Scaling vectors does not change the angle between them, right? So if I have V to be orthogonal to W, then CV will also be orthogonal to CW. If I change the length of it, if I just scale the vectors, the angle between them does not change. So what I have done here is just multiplied by some factor or divided by some factor, which is the same. So the orthogonality remains preserved, but now I have to check the length. But by definition, I have divided by its length. So its length should be 1. And you can clearly check that it is 1, right? Each of them has length 1. Is that okay?
Yes.
So through orthonormal, what we are doing actually, we are just
Yeah, that will come to.
Okay.
Why orthonormal is preferred?
Yes, actually, question is what we achieve through
Gain
this.
by doing this, yeah.
Yes.
Yeah, we'll see that.
One
So,
doubt from the lecture. In lecture, during professor told to check the orthogonality, we do the dot product. You have two
Yes.
type of dot product. They told normal and another one is a general type. What is general type?
General type is the inner product that we have been saying. So everywhere where I'm giving you the results, I'm just giving it in terms of an abstract inner product. Right. So inner product is something that we discussed last time. It is any function from V cross V to R which satisfies 3 axioms. One which I called, if you remember, if you were there in the session, positive definiteness, symmetry, and bilinearity. And this, all of what we are talking about holds for arbitrary inner products. But when we are dealing with examples, we do it with the standard dot product. Dot product is an example of a general inner product. You can do it for any inner product as well.
Okay.
Maybe at the end, we'll take up an example of, just for the sake of it, an example of non-standard inner product or not something which is not the dot product.
Okay. Okay.
Sir, non-standard inner product will be given over there, right? So the definition of the inner product where we have.
Yeah, in the problem, it will be given that consider this vector space with this inner product. If such a statement is not there, you can assume that you are working with a standard dot product.
Okay. Yeah.
By default, it is standard dot product, but the theory is available for any inner product. There might be situations where a non-standard inner product is more beneficial. In that, I cannot give you reasons now why or when, or I cannot justify that statement completely. But know that this theory has its merits, that the non-standard inner product also matters in some situations. And all of the results that we have stated hold true for that also. So orthogonality implies linear independence holds for any inner product space. It is not something that is specific to R3 with or Rn with the standard dot product. And you can get orthonormal set from an orthogonal set is also something that is true for any inner product space. All right. So that's an orthonormal set of vectors. So if you have an n-dimensional space and you have n orthogonal vectors or orthonormal vectors, what do you have? What do you essentially have?
Or linearly independent vectors?
Yeah, linearly independent, but I have a space of dimension n and I have n vectors, n linearly independent vectors, which means I have a basis, right?
And
Sir, could you repeat your
the
question,
length
sir?
of each of them is equal to 1.
So if the dimension of my vector space is n, and I have a set of n orthogonal vectors, then what is it? It is linearly independent, yes, but it is a set of n linear.
Orthonormal basis, I guess, sir.
Yeah, it's an orthogonal basis. If it is said to be orthonormal, then it's an orthonormal basis. So if you have enough orthogonal vectors, you will get a basis. So coming back to this, what I was trying to hint at when I was talking about this maximal orthonormality is, so since you have three vectors over here and it's an orthogonal set, it becomes a basis. So you cannot add one more vector and expect orthogonality to remain, because then you would have a set of four linearly independent vectors, right? So that's not possible because you are in the space of dimension 3. And similarly over here, since you have two vectors which are orthogonal, you will get at least one more orthogonal. You will get exactly one more, well, up to choice, up to scaling, you will get one more orthogonal vector to complete this. But the recipe to manufacture it, we will see later on. So this is about what is an orthogonal set, what is an orthonormal set, and all that, and what does it imply. One of the things that it implies is linear independence, or linear independence only is something it implies. It does not imply linear dependence. If it is not orthogonal, it does not mean it's linearly dependent. But if it is orthogonal, it is linearly independent. That is one advantage. The other advantage, perhaps what would seem like the more important advantage, is the following. Suppose V1 up to Vn. Right now on, shall I write On? Yeah, for orthonormal I'll write On. Okay, is an On set, is an orthonormal set, orthonormal basis of some vector space V of dimension n. Vn just means it's of dimension n. It's just a vector space V of dimension n. Now, if I take an arbitrary vector V, what is it that I can write it as? What
Linear
is the use of a
combination of,
basis? Yeah, I can write it uniquely as a linear combination of vectors from this basis. So it's like C1 V1 plus C2 V2 plus Cn Vn. So this coordinate representation of any vector in terms of its basis, you have seen it is used in the matrix representation. The matrix representation is what? The columns are given by the coefficients of the image vectors of a basis and so on. So these coefficients, finding out these coefficients are important. And typically, how would you go about finding the coefficients?
Sir,
Yeah.
sir, how do we know that the orthonormal set is minimally spanning? Because that is another condition, right, for verifying whether
It's
it's
an
a basis.
equivalent condition. I'm saying that it is maximally linearly independent. That is also okay. No? So I just need to use one of the criteria.
Okay.
I gave an argument
Sir,
for why it is maximally
Ci
linearly
inner product
independent.
of Ci Vi to itself to Vi.
No, don't let's forget about inner product for a moment and say you have such, if you have to do this exercise in a normal setting. Assume that you have some Rn where all these vectors are. What is the thing that you have to do to find out this CL?
We'll get some equations, right? When we'll
Yeah,
come
it's a
to the
system of equations again,
what?
because these
We have
will
to
all be
take them as
vectors.
alpha, beta, gamma, right, sir?
We have to
Yeah,
solve all of
you
it,
can
right?
you can leave it as C1, C2, Cn and treat them as variables also. It's the same thing. And you will be setting up a system of linear equations. You will have a vector with some numbers over here, v1, v2, v3, all of these will be numbers. So you'll get equations in terms of C1, C2, Cn, and you'll solve the system of equations using Gaussian elimination or whatever. This is how you would go about doing it in the usual order of things. But now that we know, now suppose we have this information, that the basis that we are working with is an orthonormal basis, the advantage is that if I take inner product with, I'll start out with V1. It is the same for every other Vi on both sides. What happens to this side? It is just inner product of V with V1. What happens to this side? It becomes C1, inner product of V1 with V1. It is something similar to the proof that we saw earlier. C2 plus C3 times inner product of V3 with V1 and so on up to Cn times inner product of Vn with V1. So what's the obvious next step? We keep the left hand side as it is, but what happens at the right hand side?
Except the first term, all of them become 0.
Yeah, except the first term, all of them become 0 because it's an orthogonal set. So V2 with V1 is 0, V3 with V1 is 0, Vn with V1 is 0, everything is 0 except the first term. So all of these guys become 0. What will remain is C1 times, what is the inner product of V1 with V1?
1.
Norm of
No,
V.
yeah, normal.
It's norm
That
of
is
This
V1
is
square,
an
but that is
orthonormal.
1.
Yeah.
So this is C1. So you got the first coefficient just by multiplying V with V1, inner product of V with V1. So if I do the same exercise with taking inner product using V2, I'll get that. I'll just write similarly V2 is C2 and so on to Vn is Cn. You see the coefficients you get, coefficients of a vector can be obtained just by taking the inner product of the given vector with the basis vectors. Let's see an example of this to make this more clear. What was the earlier inner orthonormal basis that we produced? Square 1 by root 2, 110, 1 by root 2, 1 minus 10, and 001. This one we had seen that this is an orthonormal basis. Suppose I want to see what is the representation of, I don't know, 563 is something times, okay, let me call this guy V1, V2, V3. I want to write this as C1 V1 plus C2 V2 plus C3 V3. So if I want to get these coefficients, what I'm saying is C1 is actually just 11 by root 2. C2 is just minus 1 by root 2. And C3 is just 3. So how did I get this? Just by using the above formula. I have to just do inner product. In this case, it's just dot product. So for I'll just do C1 and the rest are the same. I have to take the inner product of the given vector with the first vector, which is 110 divided by root 2, or I'll just put the 1 by root 2 outside over here. And this is just what? 5 plus 6 by root 2. This is 11 by root 2, and so on. So I get the coefficients quite easily if I have an orthonormal basis. Otherwise, what did you have to do? You would have had to do something like C1 plus C2 is equal to 5 by root 2 also is required. And you'll have C1 minus C2 by root 2 is equal to 6.
Yeah.
And C3 is equal to, okay, C3 you would still get for free, but yeah. This would, and you see that if this was not like a 001, this system would be complicated and go into Gaussian elimination. Whereas using this property that the coefficients of the linear combination using an orthonormal basis is obtained simply by, so the ith coefficient is the inner product of the vector with the ith basis vector. Remember, this is only for orthonormality. We have used the orthonormality very strongly. We have used orthogonality over here. We have used unit length vectors over here. So the coefficients of a vector in terms of an orthonormal basis is just given by the inner product of the vector with the basis elements. Is that clear? Or
Yes,
does
sir.
anything need to be repeated?
So just the last statement, sir.
Okay, so if I want to find the coefficient, say C1, all I need to do is multiply the given vector with the first basis vector. If I want to get the ith coefficient, the coefficient in the linear combination of Vi, I multiply, or by multiply, I mean take the inner product of the given vector with Vi. So the ith coefficient Ci is obtained by taking the inner product with the ith basis vector, if your basis is an orthonormal basis. Is that okay?
Yes, sir.
Okay, so this is one of the importances of orthonormal basis. So you can quickly get coefficients of vectors, which means you can quickly get the matrix of a transformation. So computations are simplified, but of course there is a catch. What is the catch? How do you start out with an orthonormal basis in the first place? Okay, in this case, it is given, you are given a basis and you are saying that this is an orthonormal basis. Sure, if it is Rn and things like that, you will have this orthonormal basis, this. But let us say, example, or this is more like an exercise because we will not be dealing with this right now. Find an orthonormal basis for, if I say x, y, z such that x plus y plus z is equal to 0. So this is the plane, right? What is an orthonormal basis for this? This is a two-dimensional thing. You can still come up with it easily. If I can make it more difficult by doing something like x, y, z, w, I can just do something like this, and it'll not be very easy. You cannot quickly just look at it and say, okay, this is an orthonormal basis for R. So coming up with an orthonormal basis is a problem. But once you have an orthonormal basis, you have advantages, is what we have demonstrated. You will get linearly independence for free, and the coefficients of any vector for free. By coefficients, I mean coefficients of the basis vectors, as in the linear combination.
Sir,
Okay.
a small,
So, yeah.
Could you just repeat the advantage of both orthogonal and orthonormal, sir, like by knowing them?
Orthogonality implies linear independence is one of the things.
Yes,
So
sir.
in certain special cases, you will get linearly independence just because of orthogonality. And orthonormality, the one of the advantage, the big advantage is that you will get the coefficients of the linear combination of any given vector just by computing the inner product with the basis vectors.
Okay, sir. Sir, in
Instead of having to,
orthogonality,
yeah,
we
go
can
ahead.
just find out that by doing the inner product, that is dot product, by having them equal to 0, we can say that they are linearly independent. Is that the advantage of orthogonal?
Yes, yes, that is one of the advantages of orthogonality.
Okay.
Yeah. In fact, you even using orthogonality, you can find the coefficients, but you'll get things like this, right? And you will get C1 is equal to V1 by norm V1 square. You can get that also, but this is much cleaner if you have and once you have an orthogonal basis, getting an orthonormal basis is not hard. Just divide by the norm of each vector. So
yes, sir.
So orthogonal to orthonormal is not a big deal. But how do we get an orthogonal basis in the first place for any given arbitrary vector space? So you can try for this maybe, and you can tell me if you can quickly come up with an orthogonal basis for this. Maybe you can. I don't know how difficult it actually is, but there is actually an algorithmic approach, which we will see in the next session. But for now, we will take kind of a digression. It's not really.
Sir,
It's yeah.
can we just keep on putting 1 and 0 alternatively for
So
each
if you take
for
one
each
zero
term?
zero zero, this is not even in the space.
Yeah, like 1 0 and the last one will be minus half.
Minus half. Okay.
Yeah. Then again 0
Zero
1
one zero minus
0
half.
minus
But
half.
these will not be orthogonal to this.
Sir, dimension is 3. Can we say
Yeah,
that?
right.
Dimension is 3 is something that you can say just by looking at it. No, it's a plane. It's a
Yeah.
hyperplane in
Yes.
R4. So it's like one of them can be written as the in terms of the others. So dimension is 3. That's okay. But if you can you find an orthogonal basis or an orthonormal basis just by looking at it? I don't think so. You can try like tricks like that. Yeah, that's actually a very natural first guess. Whatever you said, like 100 minus half. When then you quickly understand what the problem is. If you have 010 minus half, then they fail to be orthogonal to each other. Right?
Answer any orthonormal basis is any orthonormal set is not a basis, right? It has to be maximal, right?
Right. Yeah. So you
Yeah.
you need to give me three orthonormal, three vectors which are which form an orthonormal set. Only then it's a basis.
Yes.
A maximal orthonormal set is a basis, or an orthonormal set which has the dimension of the space that you're working in, that is a basis. Not any orthonormal set. Because if you take any just unit vector, that's an orthonormal set. Single vector sets are always linearly independent. They are orthonormal because there are no distinct pair of vectors, right? So,
Yes.
so this is for later. We will see. We will revisit this specific example. If someone can remember this for the next session, it will be helpful. X plus y plus z plus 2w. It's not too difficult to remember. Maybe I'll remember. But now we'll take kind of a digression, but this will serve as prerequisites for the Gram-Schmidt orthonormalization process, which is actually finding an orthonormal basis for any given space. So what we will be next looking at is projections. It is related to, I mean, in some sense, it is related to orthonormal basis, but it might seem not that obvious. Now, first, let me just give the formula for u and v in V. So you take any two vectors in a given vector space which has an inner product. So in an inner product, we are always working in an inner product space for this session. So you're taking two vectors u and v in an inner product space, then the projection of v onto u is the formula for the projection of v onto u. It is denoted by PROJ. The thing in the underscore is what you're projecting onto. So you're projecting v onto u. So this is given by inner product of v with u divided by inner product of u with u times u. So it is a vector along u, and the length of that vector is given, the magnitude of that vector is given by this uh, inner product of v with u divided by inner product of u with u. So, but what is the meaning of this? So, for practical purposes, all you need to know is this. But I'll give you a diagram which helps you understand it better. Now we'll work only in R2. So you have a vector v, and suppose you have a vector u.
Sir,
Yeah.
we know that these results are true for dot if the inner product is a standard dot product, but then
Yeah.
how can we, like, is it also true for any inner product?
This is a definition which holds
Yeah,
in
that's
any
the
inner product
definition,
space.
but then any other proof that you are doing, assuming that the inner product is the standard dot
No, no, no.
product.
All of these proofs you may see. So over here also you see that this is true for any dot product. So the examples that I'm giving in the standard inner product space. But the proofs that
Yeah,
I'm giving, I'm actually doing it for general vectors, inner product
inner product.
spaces. So all the results are valid. It's just that I'm giving only examples over here because it's more familiar, and most of the time this is what is applicable.
Oh yes, yes.
Right? Okay. Now I have two vectors v and u. Suppose in R2, just assume that this is in R2. The same sort of picture will be. This is the motivation for this definition anyway. So you look at this. These are based at the origin, but I'm not going to draw the axis. What you need to understand when we talk about projection is, suppose there is a light source which is perpendicular to u. So if there is light falling over here, you look at this straight line kind of thing, this thing, which is more like something like this. Yeah. So you look at this thing, and this vector, this is called the projection. You can think of it as the shadow of the vector onto this. Of course, in R2 maybe this still makes sense. In abstract vector spaces it doesn't, but this is what you have to visualize it as. This vector, this vector which has this red arrowhead, this guy is called projection of v onto u. Let me just draw this complete red vector. Okay. So clearly it is a vector along u. It is a vector in the direction of u. So let us just see a derivation of this formula, or where this formula comes from. Assume that this angle is theta. Right? So this, whatever I want to call the projection of v onto u, this you have seen is some alpha times u, some alpha being some real number. So it's a vector along u, right? It's some scale of u. And I want to find out what this alpha is.
Sir, sorry to interrupt. Can you just explain me the projection of V onto U?
And that's what I'm doing over here. So if you have these two vectors v and u,
through diagrams. Actually, I'm not able to visualize it. As per I understood, U is the base here, and V
yes,
is the perpendicular on a U.
v is a vector,
Yeah, V is
and I'm
the
just looking at the component of v along u, if that is something that you have seen before. So if you look at the standard R2, and if you
Yes.
have a vector xy, what is the component of x in the along the x-axis?
Is x0.
This is x0, right?
Yeah. Yes.
And what is the component of that along y-axis? This is 0, y.
0,
So this is for the standard axis. But here, what we are doing is we are not projecting a vector onto the x-axis. We are projecting onto any vector. It could be slanted. And the idea is the same. You drop a perpendicular from the vector, perpendicular to the given line.
Yes.
And then you look at these two components. Right? One of them is this, one of them is that. So this red vector plus this dotted black vector.
Yes.
These are the two components. One component is along u, one component is perpendicular to u. Similar to along x-axis and perpendicular to x-axis. It is the same parallel. but here we are doing it for arbitrary vectors.
Okay.
Okay.
Yes.
So this projection of u onto v, this is some scale of u. And how do I calculate what is the, I have to calculate what is alpha, right? So if I take norm of projection of u, projection of v onto u, this will be modulus alpha norm u. But what is this? What is norm of projection of v onto u? You remember that projection of v onto u is this red vector. What is the norm of that? Norm means length, right? So I'm going to say that this is cos theta would be length of projection divided by hypotenuse. Hypotenuse is v. So length of projection is this. Do you get this?
Sir, could you once repeat 2 steps back?
Okay. So I'm trying to give you the motivation for this definition. So what I would like to call the projection is this red vector. So now I'm trying to calculate what that red vector is without appealing to the inner product necessarily. I'm just in R2 standard dot product and all that. First thing that I observe is it is a vector along u. So I write it as some alpha times u, and I have to figure out what this alpha is. Is that first step clear? Why I wrote this
Yes,
projection
sir.
as alpha times
Sir,
u?
a small sort of
Now second,
confirmation.
yeah.
Alpha is some constant which on u where it represents v.
Yes, so alpha times u would be v, the projection of v.
Projection of v on u. Am I
On
right?
u, yes.
Okay.
Yes.
Please continue.
So yeah, this is the red vector in the figure. So that's the first step. I write it as alpha times u. Now I want to find out what alpha is, if possible, in terms of v and u. So I take the norm on both sides. The norm of alpha u will be modulus of alpha norm u. And this modulus I'll just remove because here I know that it is a positive constant. For negative constant, your cos theta, the signs of cos theta will just balance each other out. But what is this norm of projection of u? So this is this red vector, right? So in this, I'm just drawing that triangle over there. So this was your projection of v onto u. That was this. And this was theta. And this was v. This was projection. So length of projection divided by length of v is cos theta because it is adjacent side by hypotenuse. Is that okay?
Once again, could you say, sir? Like I missed.
So in this triangle, cos theta is equal to norm of projection of v divided by norm of v. Because projection of v is the adjacent side and v is the hypotenuse.
Yes, sir. Got it, sir.
So norm of projection of v is just norm v cos theta. But what is cos theta? Theta is the angle between v and u, correct? So what is cos theta?
Yes, sir.
U dot v divided by norm of u norm of v.
So this is just, in this step, I've just removed cos theta and replaced it with u dot v divided by norm u norm v. And norm v is 0, so is not 0. So I can cancel this out. And what I get is that I bring the norm of u from that side to this side and get that alpha is actually by norm u square. Is that fine? So 1, 2, 3, 4, 5. So there's 5 steps. Is there doubt in any step?
No, sir.
All right. But what is norm of u square? I can just write it as u dot u, right? U dot u is norm u square by definition.
Yes, sir.
So I got the value of u in terms, value of alpha in terms of u and v. So coming back to this guy, what can I conclude? I can conclude that projection of v onto u is u dot v divided by v dot v times u. So this is generalized to the arbitrary inner product space setting. And we have, instead of dot products, we use the inner products that are available to us.
So this u dot v is basically the inner product, right?
Sorry to interrupt you, sir. Yeah, here alpha
Yeah, so
value,
here
it should be
here
denominator should be u by u, and then the when you substitute the value, say you have put it vv. So here you
Which
have
where?
calculated.
So it's the definition of projection. So
Alpha
I think
you
you
have
wrote
given-
right just right now. The
So
denominator
here,
part, u dot u.
So alpha you have written that u
At the ending, I'll tell, sir. At the end, sir.
yeah,
In the formula, a projection of v, not in the
Just
formula.
above fifth point. Just above fifth
Ye-
point.
Yes,
okay,
sir.
okay.
Yeah.
Okay, there was
yeah,
type.
that is what
Yeah.
I'm saying, sir.
Okay. Yeah, thanks for that. So here what I did was I gave an idea of where this formula comes from, motivated by the geometry of R2. And then I said that for arbitrary vector spaces, inner product spaces, this is the formula which is just using this formulation. I've just, instead of dot product, I've replaced it with the inner product available. And this is called the projection of u onto v. Is that fine?
Fine, sir. Fine, totally fine, sir.
Okay. So for practical purposes, all you need to remember is this formula. V dot u divided by u dot u, or inner product of uv divided by inner product of uu times u. So if you're projecting onto u, you will get something along u. So even that is not something that you need to necessarily remember, but this coefficient is something that you need to remember, but even that is quite natural if you look at it in a certain way. I don't want to confuse you further, so I'll not give you that other formula. Just remember this. This is what is required. Now, this was projection of a vector onto U. Next, we'll see what projection of a vector is onto a subspace. So here we just had one vector, but one vector actually defines a subspace. How does it do that?
Sir, could you repeat your question?
So here we are projecting a vector onto another vector. But what we are essentially doing is we are projecting a vector onto a subspace. What is that subspace?
Sir, are you talking about the affine subspace?
No, I'm not talking about a affine subspace.
It's a line, right? It's
Yeah, so if you are given a non-zero vector, in this case u, it determines a one-dimensional subspace. What is it?
The scalar
point.
multiple of that vector.
a line, right?
Yeah, the span.
Sir, a point,
The span
right.
of u. No, it's not the
Yeah,
point.
span.
The span of u is a one-dimensional subspace, which means all scalar multiples of u. So when I say I have a vector v and a vector u, and I'm projecting it onto this u, it's the same as saying that I'm projecting onto this subspace defined by u. All right. So now we'll see.
Sir, you can just obtain the subspace by scaling the vector, right?
Yeah. So one single vector determines a one-dimensional subspace. Now, if you have two vectors, you have two cases. If they are along each other, then they determine a one-dimensional subspace. If they are linearly independent of each other, they define a two-dimensional subspace, and so on. But if you have a single vector, it determines just a line which is just scalar multiples of that vector. So you can think of this as projection of V onto U, or you can think of it as projection of V onto the span of U. It's both the same. But now, after I finish this, it will probably make more sense. You'll have projection onto a subspace W. So suppose I have a vector space V and then I have a subspace W. What does it mean to project onto the subspace? Once again, it is useful to look at the picture of something like if I have a plane in R3 and I have, let's say, a vector, I can think of this as the shadow of this thing. There's an orthogonal component and there is a component along the plane. I cannot draw this very well, so you can look it up. You can think of it as there's again light shining from above, and what is the shadow that your given vector casts? That is called the projection of that vector onto the subspace. So this vector was not actually in the plane. So if I have a vector which is not in the plane, and then I drop a perpendicular from its endpoint, and that is called the projection. That is to be understood as the projection. Now I'll give you the formula for it. So suppose W1, W2, Wk is an orthogonal basis. This is for W. Then projection of V onto the subspace W. So this is to be read as projection of V onto W. This is given by summation I going from 1 to k, projection of V onto Wi. So in order to go from one projection onto a single vector to projection onto a subspace, what we do is we consider an orthogonal basis for W and then project it onto each of its basis vectors. It has to be orthogonal. It's an important thing. If it is not orthogonal, it will fail. This is not, that will not be the correct definition. So what is this quantity? You already know. It is given over here. And what you need to do is take an orthogonal basis, project the given vector onto each vector of the orthogonal basis, and then sum it up. What you will get? Sorry, could you repeat
No,
what
sir.
you were saying?
No, sir. I was just following you. No problem.
Okay. Yeah. This is called the projection of V onto W. Now, a special case is if it is orthonormal. If this is orthonormal, then what happens? Well, the formula doesn't change because orthonormal sets are orthogonal. So I'll use the same formula. Projection of V onto Wi. But then let's see what happens to projection of V onto Wi. What is the formula for projection of V onto Wi?
Inner product
Do you
of
remember?
U dot V.
Yeah. Well,
Divided
V
by,
dot Wi in this
sorry.
case.
Sorry. W dot W.
Wi
Times
dot Wi times Wi. But what is Wi dot Wi?
1.
So this would just be V dot Wi. You can remember this specific case for orthonormal vectors, or you can just remember this and it'll be good enough. This is one. Yeah. Wait. Okay. And this is the other. This is for, remember that this is only for orthonormal and this is for orthogonal in general. Okay, so that's how you calculate the projection of a vector onto a subspace. So let's take sort of a trivial example. Let's take 2, 3, 3. Projection of onto xy plane. So if I want to calculate the projection of a vector onto a plane, what is the thing that I need?
XY basis.
A basis, not just any basis. I need an orthogonal or orthonormal basis. But this is the xy plane. This is in R3. So you have a natural choice of an orthonormal basis. What is it?
1, 0, 0 and 0, 1, 0.
So this is an orthonormal basis for the xy plane. So that's why I said that it's kind of an easy example, because so far we have not seen how to construct orthonormal basis. So let's just work with this. And so what would be projection of, let me just call this guy xy, okay? Projection of 2, 3, 3 onto the xy plane. This would be, can you continue? Can anyone continue?
2, 3, 0.
It should be, yeah, but let's go step by step. No? It's projection of 2, 3, 3 onto 1, 0, 0 plus projection of 2, 3, 3 onto 0, 1, 0. So I take each of the basis elements of an orthogonal basis and project onto them and sum them. So projection of 2, 3, 3, 1, 0, 0 is just dot product of 2, 3, 3, 1, 0, 0. Okay, maybe I'll write that too, since this is the first time. There's a divided by norm of 1, 0, 0 whole square. But since this is the first time, again, I'll write it. So this is times 1, 0, 0 plus 2, 3, 3, 0, 1, 0 divided by norm of 0, 1, 0 whole square times 0, 1, 0. So this is 1, this is 1. So those will not appear in the next one. What is the inner product of 2, 3, 3 with 1, 0? 1, 0, 0. That's just 2 times 1, 0, 0 plus 3 times 0, 1, 0. This is 2, 3, 0. Is this fine? Is this okay?
Yes.
But this should not be too unexpected, is what I'm saying, because if I have R3 and let's say this is X, Y, Z, your 2, 3, 3 will be something like 2, 3, 3, something like this. It will be some vector like this, and you're projecting it onto the XY plane. So of course you will just lose the height because you're shining light from the Z axis, because XY plane is your plane. So you have to, your light source is in some sense perpendicular to the XY plane, which is in the Z direction. So all it kills is the height. So the shadow of 233 has to be 230.
Sir, could you once again explain, sir?
Okay, so when you're projecting onto a subspace, at least in R3, if you're projecting onto a plane or a line, well, in a line it becomes slightly different because then there is not one direction which is perpendicular. Let's take a plane. If you have a plane and if you have a vector not on the plane, the projection can be thought of or visualized as the shadow of this vector when light falls from a direction which is orthogonal to the plane. So in this case, what is the direction orthogonal to the xy plane? it's the z direction.
Yes, sir.
So
Right.
the
So
vector is
when
in YZ plane, sir? The vector, original vector
no,
for which,
no. This is 233. So that's why I cannot draw this properly. It is suspended, but yeah, it's a two-dimensional diagram. So just think of it as 233.
okay,
And then when there is a light coming from above, the shadow will lie on the xy plane, and nothing like these 2 3 don't get distorted. The first 2 3, only that z component becomes 0. In other words, what I'm saying is, what you can check if you want, check projection of xyz. It is not much of a check onto the xy plane, is just xy0, and this just agrees with our intuitive understanding of projection being in some sense the shadow of uh, the vector onto the space.
Sir, can we say only with the basis vector, right?
Only
Directly,
with what basis vector?
like standard basics vector. Since we have taken only 1 0 0 and 0 1 0.
No,
It would work for anything. So this projection is independent of the basis, which
so
No, I'm
maybe.
not.
so if
Only values, sir. I'm talking about the values of x, y. If 2 is taken
No,
instead of
xyz
1,
is just a.
then it would
Which two is
change,
taken
right?
instead of one?
Yes, instead of 1 0 0, 2 0 0, and 0 2 0, then the answer would be
Okay, let's do it
multiplied by
that
2,
way.
right?
but that is not orthonormal then. Like
It's not orthonormal, but the orthogonal. Let's take this 2 0 0 0 2 0. You're expecting the projection to be different.
Like the value of the projection to be multiples of.
no,
Yeah, that doesn't happen. So this is still the xy plane. So I'm using this basis instead and using the same formula. So this will be projection of 233 onto 200 plus projection of 233 onto 020. Now when I take the dot product here, I'll skip some steps, okay? Because
Would still
we
be
are
2
kind of
0.
running out of time. It should be. It will be.
Yes,
So
because we can
233
multiply.
times 200 is 4. That is the projection, the numerator of the projection, the coefficient of the projection, divided by norm of the thing that you're projecting onto, which is 2. 2 square, which is 4, times 200, plus this would be 6 divided by 4 times 020. You can check this. I've just skipped through the thing. And this will still be 230, correct? It should be.
Yes, yes.
It is, yeah.
Sir,
So,
I'm
yeah.
having a small confusion in norm. Sir, we should take
Hmm.
root over 2 square, no, sir. Calculating a norm. Am I wrong?
Yeah, but here you have just u dot u, which is norm u square.
Oh, okay. Oh, sorry. Okay.
Yeah, so here you have this u dot u, no? It's not
Okay,
Sir,
got it.
norm of u, it's norm u square.
Yes, sir. Clear.
sir,
Yeah.
so it is not compulsory that we have to take a basis from that subspace, right? We can just take any vector, right?
You can project any vector onto the subspace, that you can take any vector, but these guys, these have to form an orthogonal basis. So when you're trying to do the computation, you need to work with a basis, and that of course has to be of the space that you are projecting onto.
Okay, so we have to use a basis and that has to be orthogonal, right?
Yes.
Okay.
As long as it's orthogonal, projection onto first one plus projection onto second one will work. Second
So
one, or if there are more,
if
then
I
more.
take a vector from that if I take a vector from that subspace which is not a basis but is orthogonal, so will it work?
What do you
Will it
mean?
yield the same result? I If we use a if you use a vector from the given subspace, which is not a basis, but then it is orthogonal, then will it also
Orthogonal to what? So wait, okay. Just let's
orthogonal? No,
take this up.
orthogonal. Like
You want projection of V onto XY plane, where what are you specifying that V is?
V is a uh, set of orthogonal vectors from the subspace.
No, V is single vector. You have to tell me what
Okay,
that
yeah.
is, and then I can project it.
V is any random vector which is not there in the subspace.
It's not there in subspace. Like then 233 is one such example. No, 233 is not there in
Yeah.
the subspace.
Yes.
Perhaps you mean something like 230 or 003 maybe.
230 was okay, sir. Like we can. I'm assuming that V is not there in the subspace.
Okay.
And yeah, and if I use a set of vectors, if I take the projection of V on a set of vectors which is orthogonal, but then it is not a basis of that subspace, then will the answer be the same?
See, you are supposed to take a vector and an orthogonal basis of the subspace.
Okay.
So if you take a vector from outside, then you cannot get an orthogonal basis of the subspace which is also orthogonal to the given vector. Like all of them cannot be orthogonal unless, well, there are conditions. Maybe you are confused about that itself. That if I take, for example,
Like I'm saying that we can take some vectors from that subspace which are orthogonal, but then they are not essentially the basis of that subspace.
no, if you have orthogonality, then linear independence follows. And if you have enough of them, in this case it is two. If you have two vectors which are orthogonal, they will form a basis. They will be linearly independent.
So let me just ask this thing, like what I've got from what you have explained so far is that we have any basis and we have made it orthonormal with that process that you told.
We have not done the process to make it orthonormal yet. I'm just giving you orthonormal basis.
Divide it by this and it becomes orthonormal. Like so.
Okay, that you can do. Yeah, orthogonal to orthonormal we can do. Yeah.
Okay, so we are assuming that there is orthonormal basis, any basis, and if we have a vector which is expressed in terms of the standard basis, now we are saying what would its components be if expressed in this new basis, right? This orthonormal basis, and this is what this process gives us.
No. The projection does not do that. The projection gives you, it does not give you coefficients. It gives you a vector, and that vector is just
that's what I'm
the
saying,
component of the given vector, which is, sorry?
I'm saying that's what I'm saying. The 2 and the 3, 2, 3, 0 is representing like this vector now in terms of this basis, right? Like
yes, that's true. That's correct.
Okay, so that is the purpose of this. Like that's what I'm trying to like.
The purpose of this is to find the component along the given subspace, and then it will be another application of this will be seen in the next session. Right now, you can just take this as formula, or you can just think of it using this shadow or what is the component along this direction and all that. So next session, maybe it will become more clear.
Sir, so basically the basis, the help of the basis that we are taking for this projection, it is basically to find the projection only, right?
Yes.
So that is the sole purpose of the standard basis in this equation, basically.
In this case, yes, but it does not matter if you take a standard basis or a non-standard basis. As long as it's orthogonal, the end result that you will get is the same. Will be the same.
So basically, we'll have to take orthogonal basis only.
Orthogonal basis only, yeah.
So sorry
but as you, yeah, go ahead.
Sorry to interrupt you, sir. I missed some parts. Sir. I was just okay with that. You for three-dimensional place, if the projection will be in the sir xy plane because we are projecting light on the xy, then that component vanishes, sir. Because for obvious reason,
Yeah.
that is the only thing, sir. After what you have discussed, sir, after that, what you have discussed, sir?
After that, I've not said much. I've just said that it is independent of the basis that you have chosen, that we demonstrated with an example. Like even if you take 20020 instead of 100010 and use the appropriate formula, you'll get the same result. So this projection is not sensitive to what basis you choose, as is to be expected. And then the next thing that I was going to discuss was that projection of any vector in the z-axis is 0.
Because we project from the we will project a line along the z-axis, isn't it, sir?
Exactly. So if you have xy plane and if you have the z-axis, and if I have any vector along the z-axis, positive or negative, so what would be its projection? It would have zero shadow, right? Like if
Because
the
the light
sun
will
is
be
above
on
my
the
head, yeah.
yeah.
So there is no
Okay.
shadow. So and
Okay.
this is verifiable using the formula as well. So here we saw that it is xy0. So if it is of the form 00z, which is something on the z-axis, then you will get 000. So you will get zero projection for
Got it.
vectors which are orthogonal to the given subspace.
Sir, so 003 example which you have taken before is 0 projection on
Yeah,
xy plane.
projection. Yeah, for any v in z-axis that is true.
Okay.
But okay, maybe 003. You can verify that this happens. This is 0.
Got it, sir.
So, sir,
Right.
if we don't take a maximally orthogonal subset of that vector space, so will the will that be a projection of the vector on the subspace?
No, I don't understand that question. Projection of a vector onto a subspace is calculated using the vector and an orthogonal basis for that subspace. So you don't have a choice of not choosing a maximally orthogonal set. For the subspace, you have to take a basis, which is by
We have to
definition a
take a basis,
maximum.
right?
So
Yeah.
maybe he's trying to ask if rather than taking orthonormal basis, we take normal basis, any
No,
normal basis.
I'm just asking that
You
whether
can't take
have to
fewer
take a
than two
basis or
vectors
not.
over here, for example. You
Yeah,
have to take a basis and project onto each basis, and not just any
yeah.
basis. It has to be an orthogonal basis.
No, in
At the
this
very
case,
least,
basically,
orthonormal
I'm asking that
easier.
if we take maybe a single vector instead of two
You cannot. You
vectors.
cannot. You cannot. You cannot.
Okay. Yes.
So the algorithm says take an orthogonal basis, right? So you
Got it,
have
sir.
to project it onto each basis vector of an orthogonal basis. So yeah, back to this point that anything orthogonal to the xy plane, which is the z-axis, will project onto 0. And similarly, projection of something like xy0. What would be projection of xy0? This is example
xy0.
continue. It will be xy0 itself.
Yes, sir.
And isn't that also sort of believable? Because if you have a plane and the vector is already in the plane, then what would be its projection? It would not have any component outside. So its projection is itself. That's also natural, right?
Yes.
Sir, if it is 2x and 2y, then also it will be like 2x, 2y only, right?
It will be 2x, 2y only.
Okay, yeah, thank you.
You're actually asking very, very correct questions. This is also a property. Is this what you were asking? Is this what you were maybe thinking about?
Yes, sir. I thought, yeah, I was confused if their, what do you call, constants get into like, yeah,
Yeah, so
I understood.
if you have a vector and it has a shadow, which is let's say this, and then if I double it in length, its shadow will also double in length. Its projection also should scale accordingly.
Yes,
Do you
sir, I
see that?
understand. Yes, sir.
Yeah.
I
To
confirm.
verify it, you have to use the formula. Whatever I say about this shadow, this light, and all that, that is just for your understanding. That is not the mathematically rigorous argument for it. If you want to give a mathematically rigorous argument for this, I think the prof in his videos has given a proof for this. Scale of the projection of a scaling of vectors is the scale of the projection of the vector. Actually, this very conveniently brings us to the next concept, projection as a transformation. Maybe I'll not explain everything in this. In the next session, I'll maybe start with this, but I'll just quickly tell you what it is. So you have a vector space V with whatever, all of these guys. It's an inner product space, and W is a subspace. So you can define a map from V to V, which takes any vector to the projection of the vector onto the subspace W. Now you know what this symbol means, right? You have to take an orthonormal or an orthogonal basis of W, project V onto each of the vectors and add them up. What you will get is projection of V onto W. V is mapped to projection of V onto W. This is the map that I'm giving. A map between this vector space and itself. A map between a vector space and itself, which is given by this. Do you understand this map? Do you understand what is happening in this?
Yes.
Yes, sir.
Right. It's just what is the input, what is the output. Now, some facts. I say facts because I'm not going to prove all of them. Yeah, I don't think I'll prove any of them. Projection. You can also call it projection onto W. Sometimes it is also denoted by PW. So I'll write PW or projection onto W. Whatever is standard notation, you can check from the lecture notes what is the convention that is followed. This is a linear transformation. So what does it mean to say it's a linear transformation? There are two things that need to be checked. One is sums of vectors go to, like the projection of sum of vectors is the sum of the projection of the vectors. And the scale of the projection of the vectors is actually this projection of the scale of the vector. So these are the two things that need to be checked. And I think, yeah, the prof has given a proof for this as well. I'm not going to give the proof. You can check that if you want. But know that it is linear transformation. So as soon as you have linear transformation, what are the two things that you're interested in? I think it came up in the beginning of the session as well, in the form of a doubt. The two spaces associated to a transformation.
Visual addition and scalar multiplication.
No, two subspaces which are associated to a linear. Yeah, it's the kernel and the image. So what do you think is the image of projection onto W?
Would be a subset of projection, sir.
Subset of projection is an operation. So what do you mean by subset of projection? So what did we say over here? What do all these things say? When you're projecting onto a subspace, where do you land?
On the subspace.
On the subspace itself, right?
Right.
So this has to be W, no?
But if it's perpendicular, it will be 0.
Zero is still in W.
Oh, yes, correct.
Sir, a small confirmation.
Yeah.
Sir, image is the range of the subspace, right? So
Yes,
that's why
yes,
you're
yes.
taking W as, since W is
Yes.
the range. Okay.
Yes. So, okay, before image, maybe I have to say this. What is projection onto W of W? So So here there are vectors in W and vectors which are not in W. So if I specifically take vectors in W, then what is projection of a vector in W onto W?
Itself, I guess, sir.
It will
Them.
be itself, because nothing changes.
So we
And you
saw
can
it in the
verify
case
this.
of
Yeah.
230, right? In that case.
In the case of XY0, we saw that it is XY0 itself. That's a specific case, but this happens in general. And if you want a proof, you have to either write it down yourself or refer to some standard book. I'm not going to go into the proof of it. But vectors in the subspace itself, they go to themselves. So the image contains all of the vectors in W and nothing else, because even if you have vectors not in W, they are projected onto the subspace. So the image of projection onto W is actually W. What is the other space that is associated to?
So this PW you have mentioned is a linear transformation, is a projection basically, right?
Yes. So projection, here we discussed projection of a single vector onto a given subspace. So here I look at it as a map wherein the input is a vector and the output is the projection of that vector onto the given subspace.
Okay, input is the vector and output is the projection of the vector into the subspace.
Yeah. So it's like P V W is projection V W. So it's like projection, instead of writing PROJ, you just write P of V onto W. So you look at it as a linear map. It's a linear map is a result. But first of all, you just look at it as a function from V to V. Strictly speaking, it is a function from V to V is not wrong, but it's more specifically it's a function from V to W. But it is not wrong to say it's a function from V to V also. It's just that it's not a surjective function from V to V. Okay, so that's about image. That image is W. What is the kernel?
V?
At least what was the kernel in the
it will be all the
specific
vectors
example?
that give
Null
zero.
space of V.
And null space of V is just another name, but do you know the description of it?
All the vectors that will be perpendicular to W.
Exactly. So that is called W perp. So how is it defined?
Sir, could you give an example? It's a bit confusing.
The image part is okay. No, it's for the kernel that you want the example.
Yes, sir.
So this is. So first I'll explain what W perp is. W perp is the set of all vectors in the space which are orthogonal to all vectors in W. Okay, so the specific example here we have already seen that z-axis, any vector on z-axis projects onto 0, or so any vector on the z-axis is in the kernel, correct?
Yes, sir.
And what is xy plane perp? So if you are given a subspace, there is a perpendicular subspace to it. So this W perp that I've written is actually a subspace. So what is xy plane perp? It is all the vectors, so xyz, such that xyz is perpendicular to all vectors in xy plane. In particular, you need this to be 0 and this to be 0. In other words, x equal to 0, y equal to 0 has to happen, and you can show that it's actually the precise condition. Everything of the form 0, 0, z forms the entire set of vectors which are orthogonal to every single vector in the given subspace.
I understood. I got it, sir.
Yeah. Okay.
So it's a transformation where null space is given, so that's pre-image is given, right?
The null space of this transformation is the set of all vectors which are perpendicular to all vectors in W.
Yes, sir. I got it.
And the image
sir.
is W. So as a
Sir,
consequence,
what was the image is W? Once could you repeat that point, sir?
So projection of any vector onto W lies in W, no?
Yes, sir.
So you see this, you write it as a linear combination when you're writing this. Take for example this. You're writing it as a linear combinations of Wi's, and these Wi's are in W. So all the projections are in W. So
yes, sir.
Irrespective of what vector you take, you will land in W, which means your image is a subset of W. But then W goes to W. Projection of any vector in capital W is just itself. So actually every vector in W is the image of something.
Yes, sir. I understood. You were explaining
Okay.
point 2 and 3, right? You wanted to say. Am I?
Yeah.
Okay.
So this
I
is
thought.
V to V.
Sorry. Yes, sir. Got it.
And you have W inside this and W inside this also, right? So this is mapped identically onto itself. W is mapped to W, but then things from V also come to W. Maybe that's too messy. You see, this is identically mapped to itself. But vectors in V is not mapped to a vector outside W. It's also mapped to something inside W itself. So the image of this transformation is actually equal to W, and the kernel, which is the guys who go to 0. What vectors have 0 projection? The vectors which have 0 projection are exactly the vectors which are perpendicular to all vectors in W, which we denote by W per. Right?
Yes, sir.
So what is the dimension of W per?
Same as dimension of W.
So in this case, your W was XY plane, and XY plane has dimension
2.
And its perp was
Perpendicular z axis, 1 dimension.
It will be a plane.
That's 1 dimension. So it is not equal, correct?
One minus that, I guess.
It's not 1 minus that. The clue is rank nullity theorem.
Yes, rank plus nullity is equal to dimension.
Sir, it's the columns. Sir,
dimension of kernel of PW plus dimension of image of PW is equal to what?
Number of basis dimension of basis. Can we say, sir?
Dimension of V. We are in this vector space V, no?
Sir, I'm confused about V, sir.
So we are in a space V and we have a subspace W.
Sir, V need not be any orthogonality. Does it have to follow some conditions, or it could be any subspace?
V is the vector space that we are in, and W is the subspace we are projecting onto. Think of it as R3 and we are projecting onto a plane in R3. R3 is the parent or the universal vector space.
Okay, I understood.
And XY plane is the plane that you are projecting onto. So the domain of my linear transformation is a vector space V, and the operation, the linear transformation, is projection onto a subspace W. So what does rank nullity theorem for the linear transformation say? Dimension of kernel plus dimension of image is equal to dimension of the domain.
Yes, sir.
Right? But what is kernel of PW? As you have seen, that is W per. And what is dimension of image? What is image? That's just W. Both are, I've just rewritten these two things. That is equal to dimension of V. So dimension of W per is dimension of V minus dimension of W. So it's like codimension. So if you have a plane the if you have a plane in R3, the orthogonal complement of that will be a line. If you have a line, what is the orthogonal complement of a line?
A point.
Now, what does this say? Dimension of W perp will be, so if your W was a plane, this would be 2, this would be 3, and this would be 1.
1. So 1.
So if I take W to be itself a line in R3, what would be its orthogonal complement?
A plane.
Yeah, plane.
It should be a plane, right? And is that not obvious? So if in some R3 you take some one-dimensional space, there is this plane which is orthogonal to it. Of course, I cannot draw it properly. If with the coordinate axis, it is easier. If I take, say, example, y-axis, what are all the points which are x, y, z should be okay here. Hi. So x, y, z. And if I take y-axis as my one-dimensional subspace, what are all the vectors which are orthogonal to it?
The xz.
It has to be the xz plane, right? So the entire xz plane. Any vector in it would be orthogonal to it. So this angle would be 90 degrees. If you want to see this better, you know, use some graphing tool and see. But yeah, it should be. It is quite easy to see that the orthogonal complement of the y-axis is xz plane. Of course, to analytically prove it, you can just take something like 0, y, 0, which is a point on the y-axis, and take the dot product with something in the xz plane, which is of the form x0, z. And of course, this will give you a dot product of 0. So trivially, you can verify, and of course, you can also see. And it is better to see to understand better. All right, so these are some of the properties. Yeah, and then there's this PW square is PW. So, you know compositions of linear transformations? Do you know compositions? I don't think it was discussed, but it's just a composition of functions. So if I have a function from P to V, and then I have, say, F and G, then I can do G of F, right? I can take F, look at its image, that becomes the input for G. So you can get what G of F is. So in this case, you have PW, and I apply PW on it again. So doing the same, doing it 2 times is the same as doing it just 1 time. Why? Because whatever vector there is, it goes to some vector in W. So, but vectors in W are mapped to W itself. So the second time, there's nothing additional changing. Don't need to think too much about this. Just try to understand this. If you don't get this, you bring it up in the next session in the beginning. I'll most likely start with these properties again.
Sir, is this superscript 2 like a square or what?
It is a square. It is PW of PW.
Okay.
Sir,
So
I'm
I do
having
PW.
Yeah, please continue.
Just one moment. Let me complete this. If I do PW of V, I'll get PW of this vector. What essentially I'm doing is I'm doing PW of V. That is a vector in V. I'm doing PW of that again. But the thing is that PW of V is already in W. And I know that any vector in W goes to itself. So when I do PW of a vector in W, what I end up with is that vector itself. So that's why PW of PW is the same as PW. Maybe this was confusing. We'll take it up in the next session.
Can you write the projection as like how we used to write in the linear transformation chapter as a T of something? Like how would you express it if you had to express it as T of something? Like
so. For specific examples, maybe I can write that, but here it is the general thing. No? Maybe I'll start with specific examples in the next one. We definitely need to do examples, and it's already past 10. So
Sir,
we'll start with examples of projections transformation in the next
sir,
sessions.
could you just explain how without the standard basis, if you multiply the vector, why isn't the function coming?
Oh, that I'll explain.
1 minute, sir. I'm having two confirmations over here. I would like to ask.
Yeah.
Sir, we have taken over here W as a subspace, right, of V.
Yes.
I would like to ask, is W orthogonal or orthonormal? Does it validate that?
No, W, what do you mean by a subspace, like being orthogonal to what?
To itself, like there are vectors in the subspace, right? Will they be orthogonal to themselves? Is it compulsory?
No, as in that I don't understand that question because say, okay, let's take an example. A subspace, you can take it as XY plane. What do you mean by are there vectors orthogonal to
themselves? 1 0 0 0 and 0 1 0 should be.
So are you asking if every subspace has an orthogonal basis?
No. I'm confirming over here in this example. We are choosing W as a subspace of V.
Yes.
Particularly in the W subspace, elements should be orthogonal or orthonormal since they are projections, they are following projections, right?
A subspace has infinitely many elements. So think of XY plane. XY plane has elements which are orthogonal to each other. Subspace has elements which are not orthogonal to each other. And any infinite set cannot be an orthogonal set because it would imply linear independence, right? Orthogonality. So for the calculation of projection, we do take an orthogonal basis of W, but W
yes,
itself need not be a finite set because it's a subspace.
Yes, sir. I was I meant the basis. Sorry.
Yeah. Well, projection of V onto W is not something that depends on the basis, but to compute it, you do need a basis. Yes, you need an orthogonal basis.
Okay. The second confirmation I wanted is in the last point where you explained for y is perpendicular to xy, I guess. XZ, sorry.
Plane. XZ plane, yeah.
Then the dimension of W perpendicular would be 2 and dimension of V would be 3 and dimension of W would be 1. Am I right, sir?
Yes, correct.
Okay, sir. Thank you. Done, sir.
Yeah. Planes are orthogonal to lines. Lines are orthogonal to planes. That is in R3. Yeah, that's correct.
Yes,
just
sir.
one moment. I'll address that matrix multiplication doubt if there are no more doubts from this session.
No, sir. You can.
Yeah, whoever has no more doubts, feel free to leave. If you have doubts, please stay behind. And if you have doubts from this session,